So here we are in lecture 10. This is actually sort of the link between the logic part of this course and the layout part of this course. So the course is called VLSI CAD Logic to Layout. And the logic stuff, we've done lots of Boolean algebra, computational Boolean algebra, representation, optimization, synthesis, lots of interesting stuff. And on the layout side, we're going to be placing things, we're going to be routing things, we're going to be figuring out how their timing works. There's kind of a link, and the link is interesting. The link is actually a step called technology mapping. And you might think that after all of that interesting two-level and multi-level optimization that we did, that what comes out is logic gates. And the answer is no. What comes out of multi-level logic synthesis is a Boolean logic network, each of whose nodes is a sum of products form. It's not gates. And even worse, it's not gates in the actual library of pieces of gate technology that you get to put on the surface of the chip. Those are things called standard cells. So to start things off, we're just going to talk about what actually happens at the end of logic synthesis and what you actually need to do to get started with layout. We're going to talk about the pieces of the optimization problem and what the problem is. So let's go talk about technology mapping.
So we are still sort of in the middle of our transition from logic to layout, and one of the things I mentioned in the last lecture is that there's really a missing step. And because of our desire to actually start doing some interesting projects with layout technology, we sort of inverted the order. So we're going to go back to this now. So just to review, what you know from the first half of the class is computational Boolean algebra, a lot of really interesting representation, some verification, some synthesis technologies. This is the so-called front end of the ASIC design process. The back end is the layout, the geometry end, and there's a big missing step, which is how do you actually go from the results of multi-level synthesis into real gates for the layout. And perhaps it's a bit of a surprise that you don't actually get real gates as the result of multi-level synthesis, and that's the topic of this lecture. This stuff goes by a lot of different names. It's most formally called technology mapping. It's very frequently called tech mapping just because it's shorter to say. It's often just called mapping. Depending on the application, sometimes it's called fitting, sometimes it's called binding, but most commonly this stuff is called tech mapping or just mapping. A nice reference for this stuff is sort of a broad reference of a variety of technologies for this stuff is the Nani DeMicheli book, Synthesis and Optimization of Digital Circuits. This is chapter 10 in that book. So let's talk about tech mapping. What is the problem? The problem is that the multi-level models is still a little bit abstract. So, you know, what happened in the multi-level synthesis technology that we talked about? We figured out the structure of the Boolean logic network. And so in my little example here, which has inputs A, B, C, D, 3 nodes in the network, X equals B plus C, Y equals AX, Z equals AD, we figured out the right high-level structure of the network, you know, what the nodes are and how they're connected. And we also did espresso-style two-level simplification on the inside of each of these nodes, the yellow nodes in the network, so we optimized them well. But this is not really gates. And the thing to just be clear about is that this diagram below, those are not logic gates. Those are nodes in a graph that has a particular kind of a structure, a Boolean logic network. There could be thousands of those bubbles in a real version of this as the result of multi-level logic synthesis. What if every one of those nodes has a half a dozen or 10 or 15 literals in its sum of products form? It's not real gates. And the question is, how do you get it to be real gates? So, suppose that you actually have a particular technology library, and suppose that this is that technology library. Now, frequently when we talk about the technology library, the library of discrete standard cells that we are allowed to use as our basic logic elements, it's very frequently just called the technology. So suppose this is the technology that I get to use. I get to use a 2-input AND gate, a 2-input OR gate, and a slightly strange-looking thing called an OA21. It's a 2-input OR gate feeding one of the inputs of an AND gate, and the other one is just a standard input to the AND gate. It's a little bit complicated. So this is a so-called complex gate in our library. The big question that we need to figure out how to correctly answer is, if I give you the output of multi-level optimization, in this case my little Boolean logic network with the X node, the Y node, and the Z node, how do we build the two functions, in this case the y function and the z function, functions of a, b, c, and d, specified in this Boolean logic network using only these gates from our library. Now I'm just drawing this picture again here in my new slide. So this is a simple example. So I'm drawing the library as a 2-input AND, a 2-input OR, and this OA21 2-input OR feeding one of the inputs of an AND gate. I'm drawing it with big curly set brackets to just emphasize the fact that it's an important object that we get to work with and manipulate and play with in order to affect our technology mapping. And I'm coloring this in yellow again just to highlight it. What we need to do is look at our Boolean logic network and say, if I only get to use this AND gate, this OR gate, and this strange OA21 thing, how do I actually take the logic function specified in the Boolean logic network and turn it into real logic gates? And look, this is just a really simple example. It's set up to be a simple example. One of the ways I could do this is I could do this example here. I'm calling this the obvious mapping, because look, you look at the logic network, the X node is an OR gate, the Y node is an AND gate, the Z node is an AND gate. Maybe we should just make the X node an OR gate with inputs B and C and connect the output of the OR gates to two AND gates. And the top AND gate has an input A and the bottom AND gate has an input D, and one of them makes Y and one of them makes Z, and that's really just pretty obvious. Now, where this stuff gets interesting is that there are less than obvious mappings, and I'm calling this an unobvious, maybe a non-obvious mapping. And in this mapping, I use two of these OA21 gates. So to implement the Y function, I actually do this as one OA21 with inputs A, B, and C. A goes into the AND gate, B and C go into the OR gate. And for output Z, I go D into the AND gate, and B and C go into the OR gate. Well, this is a little bit strange, and I'm just putting a little kind of a question mark here on top of the two OR gates. I'll even write two question marks. It would appear that I've duplicated the OR gate. Why would I do that? You know, why would I choose the unobvious mapping? And let me give you an answer. Why would you choose the non-obvious mapping? The answer perhaps is cost. Perhaps it is the case that the unobvious mapping is superior in some dimension that I can associate with a number. So imagine that every gate in my library has a cost associated with it. Maybe it's the amount of silicon area in the standard cell gate. Maybe it has something to do with the power. Right? I mean, there are all kinds of ways of creating metrics for this, but you know, low cost is better. And so I'm just putting cost numbers. The AND2 has a cost of 2, the OR2 has a cost of 3, and the OA21 has a cost of 4. These are entirely arbitrary. You know, somebody has to figure out what the right costs are. But now I've got a picture of the obvious mapping on the left at the bottom, 1 OR 2 ANDs. And then I've got a picture of the unobvious mapping, 2 OA21s at the right. And what we can see immediately is that if I put the cost values on the obvious mapping, the OR costs 3, each of the ANDs costs 3, this entire mapping costs 3 plus 3 plus 3, that's 9. But what if I put the cost values on the unobvious mapping? Well, each of these OA21 gates costs 4. And so putting two of those together costs 8. 8 is better than 9. This is a better mapping. Now, this is a quite synthetic example. This is a quite simplified example. But in the real world, where you have large Boolean logic networks and you have things that have, you know, hundreds or thousands or tens of thousands of gates in them, what the right answer is not at all obvious. You need some metric to guide you for what the best answer is. Associate a cost with all of the gates. Map so that you choose the lowest cost covering, the lowest cost mapping of the Boolean logic network onto the library. That's going to get you an answer that makes sense. So the other way of saying why you choose a non-obvious mapping, sort of the second answer, is that you know, the non-obvious mapping has better complexity. And really this is just sort of cost in a different way. So for example, your library might have a bunch of complicated gates, so-called complex gates, that are really hard to map to by eye. It's pretty easy to figure out where you can put a 2-input AND gate or a 2-input OR gate or a 1-input inverter. But I'm showing you two realistic gates here. So on the left, I'm showing you an OR and invert structure. This is a so-called OAI22. So it's a layer of OR gates connected to an AND gate with an inverter at the output. So that's why it's called OAI. And in answer to the question, how many OR gates are there and what are their structure, the reason it's called a 2-2 is that there are two such gates. That's why there's two digits there, and each of those gates has two inputs. So you see a two-input OR gate and another two-input OR gate, so that's why this is a 2-2. And let's say that that costs 6. And next to that on the right is an AND/OR invert structure, a different one, an OAI 221. Again, an input bank of AND gates, and then an OR gate, and then an invert, a bubble. And in this case, how many OR gates are there? Well, there's kind of 3. Right? The first one has 2 inputs, the second one has 2 inputs, and the third one has 1 input. And you know, kind of the obvious way to think about why I'm just drawing a wire going into this OR structure, this OR invert structure, is that this is really sort of an AND gate with exactly 1 input going into it. And what's an AND gate with 1 input going into it? It's a wire. So this is an AOI 221. Imagine that the OAI 22 costs 6, the AOI 221 costs 7. An interesting thing to note is that in CMOS, the OAI and the AOI gate structures are often very efficient at the transistor level, a bit more efficient than actually discretely using some ANDs and ORs and inverts. And, you know, for small versions of these complex gates, these things are actually sometimes a better cost match, and it's much, much more difficult to match where these things go, to technology map where these things go, which is why we need an algorithm. So, it's helpful to introduce what I'm just referring to as a mental model, a kind of a conceptual way of thinking about what multi-level synthesis does. This is what multi-level synthesis does. It structures the multiple vertex Boolean logic network well. What does well mean? It means that the number of bubbles, the structure of the bubbles, the number of layers of bubbles between the input and the output, the complexity of the logic inside each of the bubbles, pretty good. And so, following up on that, as it minimizes or as it optimizes the macroscopic structure of the logic network, it minimizes the sum of product contents inside each vertex so that the two-level form that each vertex wants to implement is also well structured in terms of the number of litterers, and the macroscopic graph structure is also good. The big important thing to note is that optimizing the macroscopic graph structure of the logic network and optimizing the sum of products contents of all of those bubbles is not logic gates. And in particular, it's not logic gates in the technology library you are permitted to use. All right, so this result actually has an interesting name, a new name, actually a couple of names that you may or may not have heard of. This is often called uncommitted logic, which is to say, I have not committed this to a particular set of gates from my technology library. It is also called technology independent, because we often call the library that we get to use the technology. And so when the stuff that pops out of multi-level synthesis is not mapped yet to the technology, we say that it's technology independent. And so I've just got a little picture down here. There's an X node, a W node, a V node. The X and the W nodes go into the Y node. The Y node is an output. The W and the V nodes go into the Z node. The Z node is an output. Just to sort of highlight this, what multi-level logic synthesis does is it gives a good global structure to the nodes, the X, the Y, the Z, the W, and the V in this diagram. And it gives a good local structure to the insides, the sum of products forms, the sum of products inside the nodes like Z. But this is not logic gates. So what does technology mapping do? Technology mapping does something sort of interesting in an interesting way. The first thing we do, typically, is we transform this into uncommitted logic that is made up of only very simple gates, but real gates. Right? So a very common way of doing this is to transform every sum of products expression inside each node into something very simple like NAND and NOT gates and nothing else. So I've got a little picture of my network from the previous page, X, Y, Z, W, and V nodes, and I've got the X node and the Y node highlighted. We know that those are sum of products two-level forms. What do? We turn the X node into NOT gates, inverters, and NAND gates. Now, one of the things to remember from way back when in Boolean algebra is that if you have a sum of products form, with AND gates for each product term and a big OR gate connecting it, you can replace every AND gate and the OR gate itself with a NAND gate, and it will all work properly. It's sort of an interesting side effect of the De Morgan laws for how complements work. And so we're going to take all of the AND gates in the products and replace them with an AND gate, and we're going to take the output, and we're going to replace it with a NAND gate, and then we'll just put inverters wherever we need the literals to be in the complemented form, and we're going to build X, the node, as real gates, but real simple gates. So we're going to build it all out of NOTs and NANDs. And then similarly, we're going to take the Y node and we're going to build that out of NANDs and NOTs. And so it's got probably a different number of products. So it's got a different number of input NANDs. It's got maybe a different number of products, and so the size of the output NAND is different. It's got complements in different places on the literals, and so then the inverter gates are in different places. But again, I can build the contents of the individual node, which is a sum of products form, simple two-level form, as nothing but inverters and NAND gates. We're going to do that for every single node in this network, and then we're going to connect things. So the X node connects as an input to the Y node, and I'm just making a kind of an arbitrary assumption that it connects to one input on one gate. It could connect to a whole bunch of different places going into the Y node, but the big important idea is that we need to make a step away from the abstract form of the Boolean logic network to something that's real gates. And our first step is an interesting simple step. We go from the sum of products forms to NANDs and NOTs, and we do that for every node in the Boolean logic network. And so what we're going to get as a consequence of that is this sort of complicated looking diagram here where the X node, the W node, the Y node, the Z node, the V node, each one of those things is replaced by some combination of NAND gates for the product terms, NOT gates for the literals that appear in complemented form, and a big NAND gate at the output to implement the two-level form, a two-level NOT NAND form for every sum of products form, and then the sum of products forms themselves are connected properly. So what I get here is one big flat, and I'm referring to that in a very particular way, okay? One big flat network of NANDs and NOTs. This is what you map. What flat means in this context is that the boundaries between the X node, the Y node, the W node, the V node, the Z node, all of those things go away. So one of the really important things to note is that it's not as though I am restricted to take the gates in my technology library and map them against the insides of every yellow bubble on this diagram. No, I take the logic function specified by every node in the diagram, I flatten it out into two-level NAND, NAND, NOT structure. I connect up everything appropriately and I throw the Boolean logic network away. This big, messy looking logic network with all of these NAND gates and inverters, this is what we map. This is what happens next. So this is our strange and complicated looking starting point. Multi-level synthesis produces, well, the first thing it produced was a Boolean logic network model with well-structured macroscopic form and well-structured sum of products form. And what we did was we, in a sort of a dumb, brute force, simple-minded way, we pushed that immediately into real gates, but very simple gates, NANDs and NOTs. This big network that I'm again highlighting on the page here, this is what we start with. This is what we're going to map. And the big and interesting question for us is, algorithmically, how do I transform this big network of NAND gates and inverters? How do I map this thing onto the standard cells in our library in some optimal way? So this is a very pretty algorithm, as it turns out. It's a very nice application of the ideas from the computer science universe to a really interesting hard problem in the VLSI design universe. So let's go see how that works next.